to a sublinear amount of bits which we can produce, and we still get the same error, well, the same order. The constant, of course, in the omega changes. And mine increase here in the constant. And then we do the trick where we now run this extractor followed by Trevisan's extractor. So we just take part of this, we use this as seed in Trevisan's extractor. And now we can extract really everything from the source. So from two sources, we can get two Ks, so say K2 and K3. And from the last one, where we've already extracted that, and since Trevisan's extractor is a strong extractor, we can recycle that. But now the error blows up because a seeded extractor can only have an extractor which is polynomial if the seed is going to be short. And then huge breakthrough last summer. It was the first paper in the classical case. So these two authors found an extractor which works for only two sources and requires only a logarithmic or polylogarithmic amount of entropy in the sources. And their paper could only produce 1 bit. And then like a month later, Lee uploaded an improvement on their work which can extract this amount, so something which is sublinear. But then with an error which is a polynomial in n. So this error, which is polynomial in n, is quite bad for us, because if you plug that into the theorem with the exponential error, we get something which is linear in log n. Luckily for us, the constant here is you can choose it. You can really get any constant, which means we can actually get any constant in front here. Because if the constant was fixed, we'd have a problem. But since here we can put any constant we want, we just need to make n big enough, and we can. So yeah, applying our theorem, we can extract log n bits from sources which have this amount of entropy. And now the trick I did by plugging this into Trevisan's extractor in quantum case, of course they do exactly the same trick in the classical case in their paper. So when they use this as a seed in a seeded extractor, and then they can extract everything basically, so all of one source and this amount from the second source, still with the same inputs and with roughly the same error, just different constants. But now if we do this in the quantum case, we have a bit of a problem, is Trevisan's extractor doesn't work very well with the seed of logarithmic length. It's fine when your seed is log squared. When your seed is log, we have these extra requirements that it's not enough for the source to have an entropy which is log in n. We need something which is sublinear in n. And then we cannot extract everything like they do in the classical case. We can only extract something which is sublinear in k. So basically we have a bad error here, which means we get a bad output length here, which means we have bad bound on the entropy here. So these sort of has this sort of domino effect the whole way along, and we have this would be nice if it could be improved. It's sort of the classical case is still better here, but still these are very nice constructions that we get from a theorem which has an exponentially bad error. So I'll go over some open questions. Well, first of all, can we have constructions with improved parameters? I mean, there's still some constructions, in particular seeded extractors, where missing some range of parameters is still missing. Second obvious question is the bound on the reduction tight? So this thing which is exponential in m, this 2 to the m, also in the case of seeded extractors, we still don't know if it's tight, and it would be really nice to have an answer to that. Okay, and now an interesting thing would be applications for these two-source extractors, because the definition seems to be a natural generalization of the classical definition, but is really a sort of theory-driven definition. You look at the definition in these theory papers and you come up with what seems right. And it would be nice to have some kind of application-driven, maybe it could be a slightly different definition, or so actually some application where does this occur naturally in applications? So, which actually brings us to the next question: what if we don't have conditional mutual information which is 0? Can we still do something? So I'll try and answer. I don't have an answer to this question, but I'll tell you what I know, what is known in the literature. Already, let's not look at the side information. Let's just look at the special case where there's no side information, and just the mutual information between x and y is not 0. Because nearly all constructions for extractors, they just assume our two sources are independent, and there's nearly no work on when the sources are not independent. So I'll just show you what we know in this case. So when they are independent, I'm still calling them Markov, even if we just have two sources. So in this case, we know that we can extract from these sources. Okay. And then there's some negative results. We know that we cannot extract from Santavasirani sources. So Santavasirani source, is a source, say an n-bit string, where we have this bound on the bits. The distribution of every bit conditioned on previous bits is close to 1/2. 1/2 plus delta is between 1/2 plus delta and 1/2 minus delta. And we know that we cannot extract from these sources. But now, so of course, natural question is, but is there something sort of between the two? I mean, this is a big set, maybe, because a definition, an impossibility result just says, if someone claims they have an extractor which can do this, I can find one point in here which doesn't work. So of course you just take the point out of the set and ask, okay, now does it work? And maybe I'll find another point. Okay, now let's take this point out and does it work? So it would be nice to sort of shrink this and try and find exactly when does it stop working? What is the structure of the sources from which we can or cannot extract? And there are sources outside of these independent sources where we can extract. Simply the following, which I've called here truncated Markov sources. You can extract from any source Pxy if there exists state Z such that entropy, conditional mutual information of X and Y given Z is equal to 0. Then you can extract roughly this amount. So this is immediate from our result, because if an adversary holds Z, then of course we know that we can extract from it. So if the adversary deletes Z, then of course we can still extract from it. And this set is actually larger than the set of independent states, because there are many states which are not independent and satisfy this property. So of course, so there are more things there, and it would be nice to have a better understanding of what happens when this condition, the mutual information is 0, is not satisfied. In particular, what about the case when the conditional mutual information is small? As you know from Omar's talk yesterday, this is not equivalent to being close in the trace distance to a state which has conditional information 0. Because the definition is, of course, robust in the trace distance. I mean, we have this definition. We say the conditional mutual information must be 0. But if we're epsilon close in the trace distance to having conditional mutual information 0, everything goes through. The same thing with the min-entropies. We don't actually have to have a bound on the min-entropy. We can have a bound on the smooth min-entropy, which are states which are epsilon close and have min-entropy. So the definition is robust in the trace distance, but it's not robust in the mutual information. That's it. Thank you.
I don't know if you know the answer, but this is just a question I thought of. So do we know that these counterexamples are there when X and Y are classical, but the conditioning system is quantum? Like, as far as I remember, these counterexamples were fully...
Count examples to what? To the
for the conditional mutual information close to Markov states, this kind of thing.
So the last thing Omar told me is he doesn't know if X and Y are classical and E are quantum. There's no special result on that.
Okay, so that might be interesting too. Okay.
Yes, you would certainly have applications directly in this case.
I'm not familiar with these extractors, but it's very interesting. So I will ask a question about the definition. Is this uniform set is always necessary? Because you always want some uniform distribution to help with this noisy, maybe weak source, right? So is that necessary, or that will increase rate or something like that?
So
your definition.
So the definition of seeded extractors?
Yeah, you always have some D bits, right? Some D bits to help. So
yes. Well, the definition of seeded extractors is always with a uniform seed. And then if you don't want a uniform seed, you need to go to these two-source extractors. So these two-source extractors is exactly this relaxation. Here we have a uniform seed, and here we have a non-uniform seed.
But what I say is that necessary. We don't use Y. We just want to extract some uniform distribution from X
without any Y.
Without Y, yeah.
No, you cannot do that. So if you only have a bound on the min-entropy of X, you cannot do it. So these extractors, they work for a whole family of distributions where the only thing we know about the distribution is this bound on the entropy. And if this is the only thing you know about your distribution, you cannot do it without a Y. However, if, for example, you know your distribution exactly, you know the precise description, then you can do it.
Okay. Yeah. Thank you very much.
Okay, so actually I have also one question. So there was also some work by Kai-Min Chung on multi-source extractors.
Yes.
Can you elaborate a little bit how this fits with what you were doing?
So it's so they have a different model of states. I'll just find mine. Right. So we had the the conditional mutual information. So what they do is they say, okay, we're going to the family of states from which we're going to extract are constructed in the following way. We start with an adversary which has side information, which is uncorrelated to anything. And then the adversary somehow is allowed to peek at X and is allowed to write something in his memory about X. And then he's allowed to peek at Y and he's allowed to write something in his memory about Y. But when he peeks at Y, he's not allowed to remember what he'd seen when he saw X. So they construct some side information like that, and they show that they're able to construct extractors in this case. Now, in the case of the strong definition, it basically corresponds to a Markov state in which we deleted part of E. So it's sort of covered by this. And then if you take their definition for the weak extractors, it isn't clear how it corresponds to this, but then they don't have any constructions either which satisfy it directly. Okay. So
how do the bounds compare? Is there some comparison?
Yes, very similar. They, whoops, where's the theorem? There we are. We have a square root. There's a square root difference. Our bounds are slightly better with the square root, but that's due to the proof technique. Okay. I believe that, since their definition is actually included in ours as a special case, then it would be possible to get the same proof, same bounds.
Okay, great. Many thanks for the nice talk. Let's thank